Hi, my name is Cullen Anderson. I'm going to be presenting on my paper with Professor Jeff Phillips entitled Robust High-Dimensional Mean Estimation with Low Data Size and Empirical Study. So first of all, what is robust mean estimation? So essentially, robust mean estimation asks the question of how do you estimate the mean of some data that has potentially been corrupted by an arbitrarily powerful adversary. So more formally, we can consider distribution X from RD where we draw n samples from this distribution here. So here, eta parameterizes our corruption, and that's the percentage of data that our adversary can corrupt. So a 1 minus eta percentage of the data is drawn from P, our inlier distribution, and then an eta percentage is drawn from Q, an arbitrary adversarial outlier distribution. So what I mean by an arbitrary adversarial outlier distribution is that this adversary has full knowledge of the true data. So if you were to draw all the data from P, the adversary can go in and manipulate an eta percentage of it as it sees fit with full knowledge of the true distribution. And so the goal here is given these n samples from X where we do not know which points were put in by the adversary and which are in the inlier distribution. We want to make a mean estimate to minimize the distance from the true mean. That is the mean of the inlier distribution P. So here's a simple example in the one-dimensional case where our inlier distribution is this like Gaussian curve here. Um, and we'd expect the mean to lie at this line. And the adversary has cut off the tail of the Gaussian and additionally added this extra cluster here, pulling the sample mean to the right. So you might be thinking, why is this hard? So in one dimension, the median is, of course, a robust estimator. So if you were to apply it to the example I just described, it would give you a robust estimate, and it would achieve O of eta error under reasonable assumptions. However, the median does not easily generalize to higher dimensions. So the coordinate-wise median is the most natural generalization of the median, um, but it would obtain O of eta square root of D error. Again, where eta is the level of corruption. And this is because it would have O of eta error in every direction. The Tukey median is a more careful generalization of the median, and this does in fact achieve O of eta error, but it takes time, exponential, and d to compute, and is hence computationally infeasible. In fact, it's an NP hard problem. Naive pruning methods don't work either. So you might think, why can't you just say if these data points are X distance from the coordinate-wise median, for example, just cut them off. And we can see that in this example here, where we look at a spherical Gaussian distribution with identity covariance. So in this case, you would expect the data to be clustered in a ball with square root of d radius. And if you were to simply place if the adversary were to simply place a corrupted cluster within this ball that the data is expected to lie in, it could pull the data eta square root of d away. This should be an eta, not a tau. Um, and so recently, practical algorithms for high-dimensional robust mean estimation have been devised around 2016. However, work has mostly been focused on theory, and there's been little empirical evaluation of methods, and have also assumed sufficiently large data size to get these nice theoretical error bounds. So we aim to fill in these gaps. So we conduct a large experimental study of robust mean estimation algorithms. So we compare how they perform across a suite of distributions with synthetic Gaussian inliers, with synthetic non-Gaussian inliers, and also with data drawn from embeddings from machine learning models, which is an increasingly prevalent setting now. We also highlight the low data size setting, again, something which is more common now. And we revise a common and critical outlier pruning step in some of these algorithms, which allows them to be extended to the low data size regime. And we additionally release a Python library to support further research and application. First, I'll discuss all the algorithms that we look at briefly. So as some naive estimators for the test, we have the sample mean, the coordinate median, coordinate-wise median, the coordinate trimmed mean, the geometric median, and the median of means. So firstly, I should say the coordinate trimmed median takes in expected corruption tau as a parameter. We'll call this parameter tau, and some of these algorithms do take it in. And it simply prunes the tau percentage of largest points and the tau percentage of smallest points for each coordinate and returns the mean. And it does this for each coordinate independently. So it's kind of a more refined naive pruning method. And the median of means splits the data into k chunks, finds the mean of each chunk, and takes the coordinate-wise median of these k means. So this is a algorithm that's very popular in the literature, also outside of robust mean estimation and in statistics in general. And we also look at some more recent estimators. So firstly, we have Lee Valiant simple. So Lee and Valiant proposed this algorithm for optimal sub-Gaussian mean estimation in very high dimensions. And this is simply for sub-Gaussian distributions. It's not for the robust statistics case. But we use it here, and we have a modified version that aligns with an informal description in their abstract, which completely prunes points determined to be outliers. We look at LRV, which is one of the two frontier papers that had practical algorithms for this case of robust mean estimation in high dimensions practically. So it's a divide and conquer algorithm that recursively reduces the dimension of the space by half and eventually takes the coordinate-wise median. We have eigenvalue filtering, which is the other pioneering paper here. And so this algorithm consists of two steps. There's a detection step and a pruning step. So in the first step, it looks at the data and it determines if it has been corrupted. And this algorithm assumes identity covariance or equivalently known covariance. And if the spectral norm of the covariance matrix, that is the top eigenvalue of the covariance matrix, the sample covariance matrix, is above a threshold, then the data is determined to be corrupted. And this comes from the intuition that if an adversary were to meaningfully corrupt the data, it would have to pull in some direction, and this would be detected by the top eigenvalue of the covariance matrix, sample covariance matrix. And then in the second step, it prunes outliers, again, based on the eigenvectors and eigenvalues of the sample covariance matrix. Quantum entropy scoring is an extension of eigenvalue filtering. It consists of the same kind of detecting and pruning step with the same detection step. However, the pruning step is different and instead prunes outliers based on quantum entropy scores. And essentially, this allows for it to look at ways that outliers may pull the mean in several directions at once, whereas eigenvalue filtering only looks at one direction at a time. Projected gradient descent is an estimator which frames robust mean estimation as a non-convex optimization problem and still finds an approximate solution despite the non-convexity. And LP-min frames robust mean estimation as a semi-definite program and uses a semi-definite programming solver to solve the problem. However, we do not include this in our graphs as it is prohibitively slow compared to other algorithms. So for example, in a table, we show that while the other algorithms run in under 1 second for a simple setting, LP-min takes around 15 minutes. So first, I want to motivate the low data size case, especially under high dimensions, which is a major focus of our work. Up to now, most work has focused on the case where there's assumed to be sufficiently large data size relative to dimensions. Why is this, and what makes the low data size and high dimensionality case so difficult? As an illustrating example, consider a d-dimensional Gaussian with identity covariance. Then even the sample mean will have O of square root of d over n error with high probability. Plugging in, we need on the order of d over epsilon squared data points to obtain O of epsilon error. For example, to achieve error of 0.01 under 1,000 dimensions, we need 10 million data points, which is of course a lot and may not reasonably be obtained in practice. Tying this back to the robust mean estimation setting, if we now imagine this identity covariance Gaussian to be our inlier distribution, then we cannot hope to achieve better than square root of d over n error, as even without the effect of the adversary, the sample mean of the inliers has error that scales with d. Then an important goal in robust mean estimation would be to obtain as close to square root of d over n error as possible, thus minimizing the effect of the adversary. This setting is increasingly important. High dimensionality data is becoming more prevalent, and the needed larger data size cannot always keep up. For example, it's now common to get data with hundreds or even thousands of dimensions as embeddings from LLMs or other deep machine learning models. Furthermore, modern models can have trillions of parameters, and in general, any over-parameterized ML setting has more parameters than data. Nonetheless, the mean remains an important quantity to compute in these settings. Therefore, for a robust mean estimation algorithm to be truly practical, we believe that should work even with low data size and high dimensions. We aim to explore empirically what is this possible, and peeking ahead, we find that recent algorithms, some needing our adjustments and some not, still often perform well in the low data size case, often achieving error close to that of the sample mean of the inliers. Now, our first step is to adapt some algorithms to the low data size case. So in particular, eigenvalue filtering, quantum entropy scoring, and LP-min all rely on a bound on the spectral norm of the true covariance matrix. Again, these algorithms all assume identity covariance. So focusing on eigenvalue and quantum entropy scoring, they use this bound when they detect if there's outliers or not. So if you assume identity covariance, you'd expect the spectral norm of the true covariance matrix to be 1. Um, and so you'd expect with large enough data that the spectral norm of the sample covariance matrix would also be close to 1. So they simply use a bound of about 1 to detect if they should prune or not. However, with less data, the spectral norm of the covariance matrix does not concentrate, and we need to account for this. It turns out that this can be accounted for in a relatively simple theorem here. And so basically what this theorem states, it's a bound on the sample covariance matrix, the spectral norm of the sample covariance matrix. And so if we have X to be our data matrix, sigma to be our sample covariance, and mu bar to be our sample mean, and assume some reasonable conditions, with high probability, we achieve this bound here on the spectral norm of the sample covariance matrix. Um, and essentially all this does is it adds this square root of d over n term, um, which becomes meaningful with low data size, but vanishes in high data size. So is not thought about in previous implementations of the algorithm. So we highlight that in the low data size case, this term matters. And when implicit assumptions are made on the spectral norm of the covariances, this can be used in the low data size case. And to discuss this a little bit empirically, we compare eigenvalue filtering and quantum entropy scoring with the original outlier detection thresholds, which are simply 1 scaled by a factor to account for the expected corruption, and our threshold derived from this theorem. So here we show a preliminary experiment, and this shows error measured as the distance from the mean returned by the estimator to the true mean of the inlier distribution versus data size over a simple corrupted distribution with 500 dimensions. Um, and we'll see here that this blue line is the sample mean, and this purple line with also a pink line behind it is eigenvalue filtering and quantum entropy scoring with our adaptation. And we see that even with very low data size, it meaningfully outperforms the sample mean. On the other hand, this red line and the green line show eigenvalue filtering and quantum entropy scoring without our adaptation, and in fact does significantly worse than the sample mean. This plot here kind of shows why using our threshold. So this simply shows the thresholds and the true eigenvalues of the uncorrupted data used in this experiment before the corruption. And we see here that this blue line represents the value of the true top eigenvalue of the covariance matrix, the spectral norm of the sample covariance matrix. And we see that it is very large with low data size and decreases sharply as data size increases. Our threshold, shown by this pink line, captures this. Meanwhile, the green line shows the original threshold used in earlier implementations of eigenvalue pruning, filtering, and quantum entropy scoring, which stays constant. And this red line shows when this bound actually holds. And we see with data size around 6,000, we start to have that threshold actually hold. But before then, it's not a valid threshold. And this roughly corresponds to when eigenvalue filtering and quantum entropy scoring start to work. That is when there is sufficiently large data size. So now we'll go on to discussing our main experiments. So that was a little preview of what our experiments look like, the first plot there. So in general, we compare algorithms as data size, dimensionality, and corruption vary, with error being measured as the Euclidean distance from the true mean of the inliers and the mean returned by the mean estimation algorithm. We set default values as data size equals 500, dimensions equals 500, and corruption equals 0.1. We note that for algorithms that take in expected corruption as input, we just use the true corruption value. But we note that we explore in the appendix that this has little effect as long as the expected corruption is an upper bound on the true corruption. And we also plot the error induced by the original uncorrupted data, which we call the good sample mean. So here we take the mean of the data before it's been corrupted, um, and then capture the distance to the true mean of the inliers. So this kind of is the best kind of error we can expect, and it matters because especially with low data size, the good sample mean is going to have meaningful error, whereas with larger data, it would converge to zero. As a first experiment, considers our inlier distribution Gaussian data with identity covariance, high dimensional Gaussian data with identity covariance, um, and unknown mean, and consider corrupted distribution where the corruption is clustered at a distance of square root of d from the true mean. So this is simply the picture we discussed earlier. Um, and because the corruption lies along where the points are expected to be, this corruption is not easily identified and is hence a good canonical test case. So this plot shows what our experiments will look like, focusing just on the error induced by the sample mean and the good sample mean. Error is shown on the y-axis, again measured as the Euclidean distance from the true mean of the inlier distribution to the mean returned by the estimator. Here, data size is varied on the x-axis from n equals 20 to large data size, around 5,000. And in other experiments, we'll also vary dimensions and corruption on the x-axis. So this light blue line, denoted as the good sample mean error, it shows the error induced by the sample mean of the inliers. That is the data before corruption. And as discussed earlier, we expect square root of d over n error here, which is indeed what we see. So with low data size, the error induced by the variance from the low data size is meaningful, whereas as data size increases, it stabilizes approaching zero. This darker blue line here, denoted as sample mean error, shows the error of the sample mean of the data after corruption. So this stabilizes at eta square root of d, as discussed in the previous slide. But with low data size, the error increases with square root of d over n. And as a reminder, the good sample mean serves as a sort of gold standard for the error that can be achieved. And we hope that our estimators match it as closely as possible, meaning that they effectively detect and remove the effective outliers. So here's that same plot now showing the error induced by all the estimators that we examined. So first, I'd like to bring your attention to the chord median, the chord trimmed mean, and the geometric median. So throughout our experiments, we'll find that these estimators, regardless of the setting, will perform similarly or a little worse than the sample mean, meaning that they do not effectively remove the effect of outliers. Meanwhile, these algorithms, LRV, eigenvalue filtering and quantum entropy scoring, both of these with our adaptation and projected gradient descent will nearly match the error of the good sample mean. Again, the mean of the inliers. Meanwhile, Lee Valiant will tend to perform a bit better than the sample mean, but much worse than the good sample mean. However, we also find that this varies a lot depending on the distribution. So there are cases where Lee Valiant simple performs near optimally. And we can think of Lee Valiant simple as a sort of sophisticated pruning mechanism. And depending on the distribution, sometimes this works. Median of means, which is not designed for the adversarial corruption case, tends to also perform pretty close to the good sample mean, but lags a bit behind the other estimators and does show more variance depending on the distribution. So this is a zoomed in plot of what I just showed you, showing up to data size equals 500. So this looks at the case where there is less data than there are dimensions. And we see that these trends are even more clear, that even with very low data size, these algorithms, again, LRV, eigenvalue filtering, quantum entropy scoring, and projected gradient descent, these recent algorithms all tend to perform very close to the good sample mean, while median of means only lags slightly behind them, and other estimators perform much worse. And now this shows error versus dimensions. And again, we see a similar trend, even as dimensions get very large, up to 1,000, twice as large as the data size, 500 here. We see that all these estimators nearly outperform, nearly match good sample mean error throughout. And again, we see the same trend as we look at error versus corruption, where here we vary true corruption on the x-axis. One notable difference here is the performance of median of means and Lee Valiant. Median of means shows some meaningful degradation, especially as we have over 0.4 corruption. And Lee Valiant, in fact, does significantly worse than other algorithms with large corruption, showing that these two algorithms are more sensitive to the specific setting compared to the more recent algorithms designed for this case. And one takeaway from all of these graphs is that throughout the settings, LRV, eigenvalue filtering, quantum entropy scoring, and projected gradient descent all tend to nearly match good sample mean error, regardless of low data size or situation, um, which which is perhaps surprising given the theoretical results only guaranteeing good error bounds with very large data size. Now we consider the case of subtractive corruption. So here we use the same inlier distribution, but now the adversary removes the eta percentage of points that are the largest in some direction once they're projected in that direction. Um, and most notably here, we see that nothing meaningfully outperforms the sample mean. In fact, they all achieve about, the best estimators achieve about the same error as the sample mean, whereas some do worse. And it's hard to see, but the sample mean is kind of obfuscated in this line with all these other estimators. Um, but we do see that, again, median of means and some of these simpler estimators lag behind. And median of means does lag behind more significantly than it did in the other scenarios, again, showing its sensitivity to distributional assumptions. So we performed additional experiments using the same inlier distribution of a Gaussian with identity covariance, using various different noise distributions, and we find the qualitatively similar results throughout with LRV, eigenvalue filtering, quantum entropy scoring with our adaptations, um, and projected gradient descent nearly matching optimal sample error throughout. Median of means tending to lag slightly behind, but varying more depending on the distribution. Um, and other estimators performing much poorer. Now we consider the case of unknown covariance. So again, the inlier distribution will be from a multivariate Gaussian, but now the covariance will be unknown. So this proves a challenge since some of the algorithms do rely on knowledge of the covariance, particularly eigenvalue filtering and quantum entropy scoring both assume that the inliers have identity covariance or equivalently known covariance. So to adapt these algorithms to this problem, we employ a simple heuristic where we scale the data by the square root of the trace of the sample covariance over the square root of D, perform a mean estimation on the scale data, and then rescale that mean estimate back up. So first consider inlier distribution drawn from a spherical Gaussian where the covariance is sigma squared I and sigma is unknown. And the outlier distribution is now clustered at a distance of square root of D from sigma square root of D from the true mean. So this follows the same idea as before, but now with covariance sigma squared I, data is expected to lie in a shell of radius sigma square root of D. So now this shows the plots using that inlier distribution, outlier distribution, and we find very similar results despite using this very simple heuristic to adapt eigenvalue filtering and quantum entropy scoring. While we do see some variance on the simpler methods. One thing of note here is that Lee Valiant actually does much better here. You'll notice that it's not here, it's actually blended in to these lines that all nearly match optimal sample error. The only time you'll see it perform worse is after 0.4 corruption and seemingly spikes. And we suspect that here, after there is sufficiently large corruption, that it breaks down and begins to mark the wrong things as outliers and performs meaningfully worse than sample mean. Also, similarly, this happens with median of means, which also spikes with larger corruption as seen in other earlier graphs. We also ran other experiments using the same inlier distribution with different noise distributions and find the same kind of results. We also tried using different choices of sigma to scale the identity covariance by, and we see the same results. And we also tried non-spherical covariance, and we also find qualitatively similar results. Although we do note that further work here is done, especially since we use a very simple heuristic to adapt the eigenvalue filtering algorithm and quantum entropy scoring to this case. We additionally examine the problem of robust mean estimation with embedding data from machine learning models. So firstly, we examine the problem of estimating the mean of embeddings of words from large language models. So to do this, we build a data set of 400 sentences using the word field to mean a field of land, and another 400 sentences using it to mean a field of study, which ChatGPT 4.0. and we extract in-context embeddings of the word field for each sentence using four large language models with varying embedding dimensionalities: Mini-LM, T5, BERT, and Albert. And so what this means is we would take a sentence such as the field was a perfect spot for bird watching, which corresponds to the field of land definition. We'd feed it through the large language model, which would generate in-context embeddings for each of the tokens, including field. And we would take that embedding of field um, and then use it as our data. And we do this for all 400 sentences for each of the two definitions, generating 800 embeddings in total. So now to explain our experimental setup, we consider data where the inlier distribution consists of embeddings of fields of study, and the outlier distribution consists of embeddings of fields of land. So the fields of land here would be the corrupting distribution. And to account for the unknown covariance, we employ the trace scaling heuristic for eigenvalue filtering and quantum entropy scoring, as we did before. And we additionally add the step of halting pruning after more than 2 tau n data points have been removed for quantum entropy scoring, where tau is the expected corruption, which is just set equal to eta, the true corruption in these experiments. We note that this step actually is important in these embedding experiments. We see that the performance without it significantly worsens. However, using the same heuristic for eigenvalue filtering does not meaningfully improve the algorithm, so we do not employ it. Okay, so here's an experiment with the large language model embeddings. This is with Mini-LM, which has 348 dimensional embeddings. And we plot error on the y-axis versus the true corruption with a total data size of 400, which uses all 400 embeddings of fields of study. And we see that the sample mean error, this blue line over here, does indeed increase with corruption, showing that adding the fields of land does indeed corrupt this distribution and pull the sample mean away from the true mean. And we notice quite different trends here compared to the synthetic case. So in particular, these algorithms that perform very well in the synthetic case don't always perform the best here. So eigenvalue filtering completely fails. LRV fails with low corruption, but actually does better with higher corruption, but still doesn't significantly outperform the sample mean. Similarly with projected gradient descent. But quantum entropy scoring achieves near optimal error and still performs best here. So this suggests some kind of sensitivity to the inliers being Gaussian, whereas quantum entropy scoring still performs very well here. It's also worth noting that median of means is also less affected by this and still performs quite well. And Lee Valiant actually also identically matches good sample error with very low data size, and then increases with corruption, doing better than it did in the synthetic case. And here is just with all four of the language models. So this shows it's the same kind of plot, but with different dimensions. So this is 384, showed in the previous slide. This is with T5, which has 512 dimensions. And these are BERT and Albert, which both have 768 dimensions. So this just shows the data size being even smaller compared to the dimensions. And so, but even with these increased dimensions, we get the same kind of results with quantum entropy scoring consistently achieving near optimal sample error, with Lee Valiant and median of means lagging behind that, with Lee Valiant also tending to get pretty close to optimal sample error. And the other algorithms that perform best in the synthetic case, that is LRV and projected gradient descent, performing much worse. We additionally verify these results over different kinds of embedding data. So we look at image embeddings, for example. So this shows embeddings of images through ResNet 50. These are 2048 dimensional image embeddings. And this is with the inlier distribution being cat images and the outlier distribution being dog images. Similarly, we feed these images through the model and take as the embedding the last layer before like the classification layer of the model. And we see here, again, the sample mean error does get worse with corruption. And we see that quantum entropy scoring performs pretty similarly to optimal sample error, only performing slightly worse than it. Median of means lags a bit behind it, whereas these other estimators, LRV, eigenvalue filtering, and projected gradient descent, tend to do worse, especially eigenvalue filtering. We do see here that this distribution is a bit different. than the previous one. For example, um, using the coordinate-wise trimmed mean or the coordinate median does much worse here than it did in the previous distribution. And perhaps most notably, Lee-Valiant simple, it does not perform as well here as it did in the large language model embedding case, where it had nearly optimal performance relative to the good sample mean. So again, this just reinforces the idea that Lee-Valiant simple does tend to depend on the distribution. So it kind of acts as like a more sophisticated pruning procedure, which happened to work in the case with the large language model embeddings, but doesn't work here as well. We additionally verify results over non-contextual word embeddings. So these are when embeddings of words are made just through how they're used through a large corpus of data. So the word field would simply have one embedding. It would not vary depending on context. So we look at these glove 300-dimensional word embeddings, and we look at this case of pleasant words corrupted with unpleasant words. So we have this corpus of words deemed pleasant and this corpus of words deemed unpleasant, and we take their embeddings and perform the same kind of experiment. And again, here we see some kind of different results, but again, we observe that quantum entropy scoring does the best again, whereas the other estimators that tended to do good in the synthetic case don't do as well. So now we consider the case of non-Gaussian synthetic data as our inliers. We follow the same experimental setup as before, employ the trace scaling heuristic for eigenvalue filtering and quantum entropy scoring, and also enforce early halting for quantum entropy scoring as we did in the embedding data experiments. So firstly, we looked at Laplacian and Poisson inlier data, and we got results nearly identical to the Gaussian inlier data case in terms of relative performance, so we won't show them here. But more interestingly, with heavy-tailed inlier data, we see some different results. So consider inlier data drawn from a multivariate t distribution with 3 degrees of freedom, and consider outliers clustered square root of d from the true mean. So this is a polynomial decay algorithm, so it has very heavy tails. And interestingly, we observe that these algorithms tend to outperform the good sample mean. So for example, you can see most notably in the error versus dimensions graph that all of projected gradient descent, quantum entropy scoring, eigenvalue filtering, and LRV outperform the good sample mean. So this kind of matches the theory that the sample mean is not the and not an optimal estimator for heavy-tailed data. And this suggests that these algorithms designed for the robust mean estimation setting are also valuable in the heavy-tailed data setting. And we leave further exploration of this to future work. Another thing of note is that the relative performance differs here. So quantum entropy scoring is not the best here, and in fact shows these errors of large variance, whereas LRV, which tended to perform slightly worse than the other algorithms, performs the best here. So again, this suggests some variance depending on whether the inliers are Gaussian or not. Finally, consider inlier data drawn from a mixture of 3 Gaussians with each component equally weighted. So we'll have 3 peaks, one at the all ones vector, one at the all zeros vector, and one at the all negative ones vector, each having identical covariance. And the corruption would add a 4th peak at the all twos vector, but clustered around more tightly, so with smaller covariance. And we notice quite different results here from the case with Gaussian inliers, reinforcing that these algorithms are sensitive to the Gaussian assumption on data and that future work is needed in this. For example, we see the quantum entropy scoring is no longer best and has quite irregular areas of error. For example, here with lower dimensions or here with moderate corruption. We also see that the eigenvalue filtering, LRV, and projected gradient descent all degrade significantly with larger corruption in a way that they did not in the Gaussian inlier case. We see that median of means and LV-sim are not as affected by this actually, and they perform quite close to good sample mean error. And then finally, we see that LRV actually does perform quite well with low corruption, such as seen here. It performs noticeably better than good sample mean. But we suspect that this is because the outliers lie in a one-dimensional subspace, so there's some special structure in this case that can be exploited by this algorithm. In conclusion, we provide a simple updated outlier filtering bound to extend eigenvalue filtering and quantum entropy scoring to the low data size regime. So this has largely been overlooked when it is assumed that there's sufficiently large data size, but we believe that's very important to the low data size regime. Um, we perform extensive experimentation across various settings of inlier data, both synthetic and from ML machine learning embeddings. And from all of this, our work demonstrates that there's value in applying robust mean estimation techniques to data, even with insufficient data size for the classic theoretical bounds. We hope that our work will inspire researchers and practitioners to focus more on the important case of robust mean estimation, high dimensions under low data size. Thank you.